About a year ago, the department bought a 3D printer, and I think we really haven't done a good job of getting the word out and kind of telling people what it can do. And so that's what I want to try to do today. So I'll start out and introduce the printer in terms of RF applications, because that's what I focus on. And then I'll move on and kind of tell you how the printer works and hopefully answer some of the frequently asked questions. And along the way, I'll show some examples of objects we printed here at CBI in the past year. And hopefully you can, think about how can you utilize the printer for your own projects. And so to kind of get your imagination going, these are just images that I pulled off the web. So you can think about using it for architecture, for medical applications, for fun, build a guitar. That was going to sound very good, but you can try it. And remember, everything that the printer produces is plastic, so it's MR compatible. So for example, an MR compatible tool like an adjustable wrench. And this is kind of cool as well because you can put movable parts inside the object. So as a coil designer, I spent a lot of time thinking about coil geometry, how the coils are placed, and so on. And that really has a big impact on performance. And in this example, we have a 32-channel head coil. And so you might think about, what is the diameter of the coils, how should the coils overlap, and so on. But actually, one of the biggest determinants in terms of performance actually is the coil former. So that means the shell upon which the coils are placed. And in this case, we're just simply limited to a simple cylinder. And that's for various reasons, because we need to construct, you need to simulate in terms of very regular geometry. But we'd really like to do something more, and I'll talk about that in a second. So the other things we have to think about, as well as the coils themselves, is really the interface and how to get the signals out of the coil and so on. And so a lot of thought goes into really the housing of the coil. So we really have a couple ways of obtaining the housings. So one way is to really rely on the generosity of Siemens and hope that they eventually relegate some of their old formers obsolete. And this is what happened to this 1.5T breast array. So it's a Siemens product. They've given it to us, and we've kind of repurposed it. No one said it was 1.5T anymore, so we've taken all the electronics and replaced it with our own custom 7T coil, and put an NYU sticker on it and call it our own. So that's one way to do it. That's really not the best, but it kind of limits what we can do. Another avenue that's probably preferable is to rely on our expert machinist, Cornell Stefanescu. I think this line appears in just about every publication that I've had here at NYU, because Cornell really has a hand in just about everything that comes out of the RF lab. So we can do some really nice work. On the other hand, these projects are very labor intensive, and as an RF group, we're building 4, 5, 6 coils per year, and we want to save Cornell's time for more and more custom applications. And again, I'll point out that on the right is a head coil, and again we're limited to a cylinder. Again, for convenience. What we'd really like to do is move more toward an anatomically correct coil. And Graham really hammered this 2 points home in this article back in those days at GH. And really the 2 key points are that to most efficiently to generate the most efficient coil, you want to do 2 things. You want to first capture all the flux. And so that means you want to fully surround the object, in this case the head, with coils. And you can't do that with a cylinder, so you need a dome former. The other thing you want to do is you want to get the coils, capture that flux as efficiently as possible. And so you want to get the coils as close as possible to the head. And so he's just stolen a design from a safety helmet. So the safety industry has been working on helmets for decades. So why not just use these designs in our applications? And I think that's really where the 3D printer comes in, because now we can build any arbitrary shape. And okay, so that leads me into the 3D printer. I tried to make this printer look really cool and flashy. It turns out PowerPoint is really crappy animation. But also, admittedly, the printer just looks kind of boring. It looks like a big refrigerator, but just bear with me, it can do some pretty cool stuff. So down at the bottom of the machine, you have these cartridge slots. And this is where the material is stored before it's printed, before an object is printed. these cartridges look like this, so they're just a big spool of plastic, flexible plastic cord. You can flex it. It is quite brittle. You can actually just snap it in there with your hands if you want. And this plastic is fed up to the top of the machine through some hoses, these black hoses here. And at this point, it's heated up during the build to about 350 degrees Celsius, at which point it melts, and you can place the plastic where you desire. So the plastic flows out these nozzles or tips, you call them. And they're pretty straightforward. You can think of this kind of like an inkjet printer tip. And this kind of, so again, the nozzle, the tips are located at the top of this oven, which is in the kind of the center of the machine. And this is on a movable arm, so this kind of swings around and lays plastic down. This is a series of time-lapse photos that we've taken during a print job. And so we've sped up, I don't know, several hours and condensed this down into a few minutes. So unfortunately, the printer doesn't run quite this quickly. But what we're printing here is the top piece of a head coil. And so what you can see, the printer kind of whizzing around doing its thing, and it's laying down material here in both white and brown. You notice the white, corresponds to the model that we've actually designed, and the brown material is just simply support material. And the support we call support material because that's exactly what it's doing. It's actually forming a base for the top portion of the helmet. So if I speed this up a little bit, here you can see finally the printer's reached the top piece. So we're printing layer by layer as we go up, and of course you can't just print into plastic into midair. You have to have something to lay it on. So that's the reason for the support material, and we don't have to do any defining in terms of where this support material is placed. That's all done in the software. So we simply define the model, and then the software tells the printer where it is supported. Each has its unique nozzle, and it's kind of hard. It's really hard to see in the video, but it's printing both at the same time. And at the same time, meaning printing one, and it's actually resting for a bit. It has to change the temperature slightly, so it goes from maybe 355 degrees down to 345 degrees. I can't remember relative which point, but they're slightly different. And so it'll change the temperature, come back, and then deposit the support, and go back to model support. You pull the object out, and it has all the support material still attached to it. This is kind of brittle. You can actually just break it away with your hands. But if it's really embedded into the object, it's preferable to have immerse it in this solution. So this is a wet station, or a clean station we have over in the wet lab, which is adjacent to the RF lab. This just consists of a big bath of sodium hydroxide. So this is very, very strong soap. So the pH scale is very basic. So you won't need to wear gloves and eye protection and so on when you're dealing with this stuff. And so it looks kind of nasty, but you just immerse your part in there, heat it up to 70 or 80 degrees Celsius, let it sit in there for 3 or 4 hours, and you pull the part out, and it has a little more support to it. So it looks very clean. It's nice and shiny, kind of medical grade looking. And so this is the object that we was printing during the video, and we printed this in 2 sections. This is kind of for patient convenience. So we have the bottom shell that lay the patient's head on the shell, and then clip the top part on. And this is kind of held in place. And so I think you can appreciate the improvement from the old design in which we were just working with a straight cylinder. Again, the new design, you have coils that are very close to the head. They're fully wrapped around the head. So that's really two key things we really want to analyze correct here. And I think we can kind of push ourselves towards the standards set by the MGH group. They've had their printer for maybe 6 or 7 years, so they've had a little bit more time to develop their models. And one of the PhD students, Boris Keel, has really taken this to the next level. So not only does the exterior look really nice, but also the interior. He's designed stands and so on for the interface electronics, like the preamplifiers and the cabling. So actually, you can print this out and have a summer student or someone that has very little knowledge of coil building do the construction for. So this is really nice work by Boris. One of the things I was kind of hesitant about when we got the printer was the software. This is going to be really a big time sink. I'm going to spend 2 weeks designing a box or something that I could build in a couple hours by hand. But actually, I was kind of pleasantly surprised So I spent a lot of time with SolidWorks. We have 2 licenses available here at CPI. And if you want to work at home or outside the CPI firewall, you might be able to download SketchUp. I believe it's free software. I haven't personally used it, but people have told me that it's very easy to use. So suppose we want to build a breast coil former. This is one of my interests. So really, you can see there's really two key planes we want to duplicate. So if you look at the kind of the side profile of the former, you have something that tapers off towards the foot, and in the front profile, you have kind of a U-shaped thing where it's something in the middle and it's curved outward toward the lateral extent. And so we can easily draw this in SolidWorks with a couple of 2-dimensional profiles. And so SolidWorks is cool because you can turn 2D profiles or curves into 3D objects. And so to do that, there's a bunch of different features. You can use extrusions or a swept base and so on. And for this, I just use a swept gloss base. It's just a built-in feature in SolidWorks. And so what I want to do is just sweep this profile across this curve. So you do that, and it looks as you would expect. Then I add a few more features, add some legs to hold the base of the coil. Maybe put a handle so you can carry it easily. And you do several steps along the way, and you get something that really looks like as you intended. So really, I think if you can imagine what the piece looks like, you can print it into SolidWorks quite easily. You can print 2 different materials: polycarbonate, which is what I've generally been working with. It's pretty strong. These are just quotes from the website. I don't know what superior mechanical properties really means, but it is very strong, at least for our purposes. We can also print with ABS. One of the problems with this is that it is no more visible. So if you're scanning with for example, ultra-short TE sequence, you will see a faint signal from the plastic itself. So typically, that's not a good thing. We can use ABS for example, for phantoms, where you can fill the plastic with water anyway, so that you don't really care about the MR signal from the plastic. And then we can blend the 2 materials together. I haven't really come up with an application for this, but it is really possible to do that. One of the big considerations we thought about when we were buying the printer is the print volume. We wanted really something big enough to accommodate human head sized object, and so we can print up to 40 by 35 centimeter cube. You may have heard of other kind of consumer level printers like MakerBot or other things that your desktop 3D printers. These are really only good for printing really small toys or something. So we really need something that's industrial strength. The resolution the printer can handle is kind of depends on the entire object. So here we printed a resolution phantom. So we just printed a series of rods with varying diameters, and then immersed the object in water and scanned it. And you can see that the printer can pretty much handle these rods at around 0.5 millimeter diameter, but there's a missing rod here, so it probably broke, and then over here it looks like these rods merged together for some reason. So I'm not really comfortable in saying it has a fixed 0.5 millimeter resolution. It kind of really depends on the build. So for example, if you take these rods and you stretch them to 10 centimeter length, I wouldn't be confident that it would get very good result. In this case, we're only building 1 or 2 centimeter rods lengthwise. So you really have to think about the whole object, not just the resolution doesn't come down to a single number. But we do have the capability to print some fairly high resolution stuff like a thread on a bottle cap, for example. And this kind of begs the question: are the printed objects watertight? And the answer is kind of. So when you print, the printer prints in kind of this lattice fashion. So one layer will print at this angle, and the next layer will print at an orthogonal angle. But you end up with all these little gaps, and eventually water will seep through it and leak out. But there's a pretty easy solution. You can just immerse the object in acetone. Actually, acetone will kind of melt the plastic ever so slightly and kind of seal up these pores. It is kind of a sensitive process because if you immerse the object for too long, even like 30 seconds, you have very thin features. Actually, you really will melt these features and you'll end up with a warped object. The other option is to use deck sealant. You might remember patio or something. So you just take a paintbrush and paint the object. And we've done this with a Phantom. In this case, we want a very thin wall, so we were kind of hesitant to immerse this in acetone because we thought it would just burn a hole right through the wall. This wall is only I think it's 0.6 millimeters in width. So patio sealant seems to work, but on the downside, you have to, I think we applied 2 coatings to this. You have to coat the object, wait a day or so until it dries, and then coat it again. So it's kind of cumbersome, but it does work. And again, I think we're kind of aiming towards something that was done at GH again. So they printed a really nice anatomically realistic head phantom. And the cool thing here is that they have different chambers for different tissues. So they have brain, eye, and muscle chambers, and they fill each with liquids representing these tissues. And you can see on the right is the MR image that actually looks really familiar. It looks like a real image. But aside from just being cool, it's actually almost a requirement at high field for coil evaluation. So at high field, the 7 Tesla, the B and E fields are really shaped a lot, not just by the coil, but also by the object inside these coils. So if we take our coil and image a uniform sphere, like in the middle, you get a B1 plus map that's totally unrealistic compared to what you would do with a human head. So this doesn't really tell us any useful information about the coil. So on the left, they have the simulation with a very realistic head model using 15 tissue types, and that really compares pretty well with the Phantom data that they have with their 3-department Phantom. So even though this isn't completely, it doesn't include all 15 tissue types, we've just got the 3 main ones, and I think it's a nice start. So I'd really like to try to build something like this here in CPL. The material cost, it can be something at least to think about. It's 27 cents per cubic centimeter, so for a head-sized object, for this particular coil, we required 1.5 liters of material, which is $400 worth of material. So I think it's it's a fair price to pay for something that's really customized and exactly what you would want. But you have to think about the fact that you're spending $400 every time you print something. So you have to really think it through before you just go ahead and go. This claims to be rapid prototyping. It may or may not be rapid, depending on your definition. So of course the print speed really depends on the resolution. So if you look at the high resolution, so-called high resolution tip, this would take 12 days to print this head coil. So it's kind of crazy since there really aren't any high resolution features on this coil. So I think we actually printed this using a T16 tip. So it's much coarser in terms of voxel size, but now you can print this in 1 or 2 days. It may seem like a long time, but it's actually not bad when you consider that you design the object in the software, send it to the printer, hit go, and you come back in 2 days and your part's done. So there is some delay, but I think it's reasonable. You can also play with the build density. So there's 3 different print modes. You can change the software. You print in solid mode, then these are the tool paths that we have on the right. In this case, it tries to fill in the entire object. You get 95% over there. So this is a 10 by 10 by 10 cube, so you expect 1 liter of material. Like I said, it does print in kind of a lattice fashion, so there are some gaps. You print in double dent or sparse mode, you can really speed up the build, and it does this by printing kind of in solid mode around the edges, but then the interior, it doesn't completely fill in the object. So you can really speed up and save some time. One of the interests is printing anatomical representations from MR data. So the MSK group had an interest in printing scapula models of the shoulder for pre-surgical planning. So they wanted to take take a print of the scapula and give it to the surgeon, and maybe they could somehow plan their procedure around this model. And we tried this, but we ran into the usual roadblocks in MRI. You really need high contrast for segmentation, so you want to have different signal levels for the different tissues, and the requirements you need even more contrast if you want to do automatic segmentation. So you don't want someone sitting there and drawing lines around each individual slice to try to determine what's bone and so on. We also prefer very high resolution, which is obviously SNR and time domain. And the reason I said 0.5 millimeters is because we actually tried to print an object that was obtained. There was an image with 1 millimeter resolution, and we printed it out. And the radiologist said, "Gee, this looks crappy. This looks staircased and pixelated and so on. It must be maybe the printer is not working properly, or just can't accommodate this kind of resolution." But actually, the problem is that this is truly what a 1 millimeter astrology scan would look like. So we can do some post processing and zero fill or filter it or do some other things after we've recorded the MR data, and then we print out the smooth version of it. But we're definitely losing some of the high resolution features that these are exactly the things you would be interested in as a surgeon. So you have to be kind of careful about this. What looks good in the screen may not actually be what you require. So if there's a way to get high resolution data directly from the scanner, that's obviously the best approach. So yeah, the bottom line is we need custom sequences and segmentation for each application. Okay, yeah, let me just talk about, there's a couple of cool applications that we built as well. This is a cable trap designed by Carl Edler from the David Holt Group in Winnipeg, and Martijn Klaus here at CBI. So this is kind of a cool thing because basically this is something we use all the time in the RF lab. We need to, for every cable we have coming out of a coil, we need to suppress the cable currents on the ground shield. And this is really a quick way to do it. We just, once we have these built, we can just clamp them onto a cable, and we don't have to do any additional soldering or playing with the cable. So this is kind of a nice tool to have when we're prototyping coils and we're really not sure if we like the final design or not. We can just put these on and go ahead and use the coil. So that's kind of a nice fixture. Melanie Freed has designed a really nice mouse imaging fixture. So this allows her to really quickly position the mouse on the bed here. So this is a bed. The mouse would lie here with the head inside this chamber where the gas would be fed to keep the mouse asleep. And there's also some clips here at the back to get the respiratory gating cables and other cables out of the back end. So that's a really nice fixture to quickly position the mouse. One of my favorites is the PTX interface box that just recently built. This is designed to sit in there's kind of a dead space in the front of the 17 scanner that this fits nicely into, so it looks almost like it's really part of the scanner. So I think that's kind of nice for patient comfort. You don't want things that are cables hanging out and things duct taped around the table. I think that makes the patient uncomfortable. So this is kind of a nice way to really organize the electronics. So these are 8 TR switches that are inside the box. And then you can also do some cool stuff like print the NYU logo in the cover, and it's kind of like embedded in